Welcome to The Explainer. Today we're diving into something you interact with literally every single day, probably without even thinking about the incredible physics behind it. We're talking about spherical mirrors. We're going to break down exactly how they work, the math that governs them, and, well, the magic of magnification. Let's get right into it.
So, think back to when you were a kid, or, maybe even at breakfast this morning. Have you ever picked up a brand new, super shiny spoon and just stared at your reflection? It's kind of fascinating, right? You get these weird, totally distorted reflections. Depending on which side of the spoon you're looking at, your nose might look absolutely massive, or your whole face might be flipped upside down. It turns out that everyday piece of silverware is actually the perfect gateway to understanding advanced optics.
Before we get bogged down in the technical jargon, let's just look at the physical shapes. If you look at the hollow inside of that spoon, the part that actually holds your soup, it's caved in. And if you hold it far away, your reflection is actually upside down. But if you flip the spoon over and look at the bulging outside, the part pushed outward, your reflection is completely different. You're upright, but you look way smaller, and you can see a huge chunk of the room behind you. Right there, you've just experienced the difference between concave and convex shapes.
Here's our roadmap for today. 1. Mirrors in our world. 2. The anatomy of concave and convex mirrors. 3. Tracing the light rays. 4. The Cartesian sign convention. And 5. The mirror formula and magnification.
All right, Section 1, Mirrors in our world.
Let's start with concave mirrors. These are the ones that curve inward, kind of like a cave. These mirrors are absolutely crucial for magnifying an image or focusing energy. When you put an object really close to a concave mirror, it creates this highly magnified, upright image. That's exactly why they make perfect shaving or makeup mirrors, and it's why your dentist uses them to get a huge, clear view of your teeth. But they also focus incoming light rays to a single intense point. That's why satellite dishes are concave. They grab weak signals from a massive area and concentrate them onto one tiny receiver. It's also literally how solar furnaces concentrate sunlight to generate immense amounts of heat.
On the flip side, we've got convex mirrors, the ones that bulge outward. These are basically diverging or fisheye mirrors. Because of that outward curve, they shrink the image, which dramatically widens your field of view. And this is exactly why they are legally mandated for the side view and rear view mirrors on cars. They drastically reduce blind spots by squeezing a much wider area of the road into one small mirror. You'll also spot them tucked up in the corners at ATMs for security, so you can easily see if anyone is standing right behind you.
Moving on to Section 2, Anatomy of concave and convex mirrors.
Okay, so every spherical mirror is quite literally just a cutout slice of a bigger virtual sphere. On the left here, we have a concave mirror. Notice how those parallel light rays hit the inner curve and are forced inward, converging at a single point. On the right, the convex mirror takes parallel rays and scatters them outward, making them diverge. But here's the cool part. If you trace those diverging rays backward, they actually appear to come from a single point behind the mirror. To talk about these points mathematically, we really need to nail down some vocabulary.
First up is the pole, represented by a capital P. This is simply the exact geometric center of the mirror's reflecting surface itself. Just think of it as the origin point right on the physical mirror.
Next, we have the center of curvature, or C. Remember how we just said every mirror is a slice of a larger virtual sphere? Well, C is the exact center of that invisible sphere. What's absolutely crucial to remember here is that for a concave mirror, C sits right in front of the reflecting surface. But for a convex mirror, C is actually hidden behind the mirror. And if you draw a straight imaginary line from the pole right through the center of curvature, you get what we call the principal axis.
Finally, we have the principal focus, or F. This is that magic spot where those parallel light rays actually meet up, or where they seem to originate from. For small aperture mirrors, this focus sits exactly halfway between the pole and the center of curvature. And that physical distance from the pole to this focus, that is called the focal length, and we represent that with a lowercase f.
All right, Section 3, Tracing light rays. So as you walk an object closer and closer to a concave mirror, the image it produces goes through some pretty wild transformations. As you can see mapped out here, when you're far away, way beyond the center of curvature, your image is real, it's upside down, and it's tiny. But move right up to the mirror between the pole and the focus, and suddenly your image flips upright, hides behind the mirror as a virtual image, and becomes hugely magnified. It's all just geometry. To actually map this out, physicists use ray diagrams. And the beauty of this, the real trick here, is that you don't need to track thousands of light rays to know what an image will look like. You really only need two predictable ones.
For example, if a ray runs perfectly parallel to the principal axis, after it hits the mirror, it will always pass through the focus. Conversely, if a ray passes through the focus first, it bounces back parallel. Find where just two of these predictable rays intersect, and boom, you have pinpointed the exact location and size of your image.
Next up, Section 4, the Cartesian sign convention.
Answer the new Cartesian sign convention. Now, please do not let the fancy name intimidate you. The crucial takeaway here is that this is literally just the standard x and y axis graph you already know from middle school math. We just place the pole of the mirror perfectly at the 0, 0 origin. The principal axis becomes your x-axis. Since we always assume light comes in from the left, any distance measured to the left is negative, and any distance to the right is positive. Anything standing upright above the axis is a positive height, and anything hanging below it is negative. That's it. It's just a basic graph.
And finally, Section 5, mirror formula and magnification.
This right here is the mirror equation. 1 over v plus 1 over u equals 1 over f. It is elegantly simple, yet profoundly powerful. So v represents the distance of the image from the mirror, u is the distance of the object from the mirror, and f, as we learned earlier, is the focal length. As long as you follow those positive and negative signs from our coordinate graph, this single formula works perfectly for all situations, for all positions, and for all spherical mirrors, whether they're concave or convex.
But finding the location of the image is really only half the battle. We also want to know its size, and that's magnification, represented by m. Magnification tells us the relative extent to which an image is enlarged or diminished. The most direct way to find it is to just take the height of the image and divide it by the height of the actual object. But thanks to the geometry of those light rays we traced earlier, magnification is also directly tied to our distances. So m is also equal to negative v divided by u.
The final piece of the puzzle is understanding what the sign of that magnification number actually tells us. If your magnification is a negative number, it means your image is real and inverted, so upside down. If it's positive, your image is virtual and erect, standing upright. For example, any real object placed in front of a convex mirror will yield a magnification that is always positive and always less than 1, which, mathematically speaking, proves exactly why your car's side mirrors always give you an upright but miniature version of the traffic behind you.
We spent this entire explainer successfully tracking light as straight-line rays bouncing off geometry. It gives us perfect formulas and beautiful predictability. But here's something to leave you pondering. In the early 20th century, modern quantum theory revealed that light isn't just a straight line. It behaves as a continuous wave, but also as a stream of discrete particles called photons. The ray models we learned today work perfectly for mirrors, but they're really just one way we try to comprehend the deeper, dual nature of the universe. So, the next time you look into a shiny spoon, ask yourself, are you looking at a geometric ray, a crashing wave, or a